Okay, now we're going to look at the software developer's view of hardware option topic and do a couple of questions within here. The first question is convert 27 decimal to binary for 1 mark. So the process is covered before a couple of times. So 1 here is our question. That is there. So, okay, so 27 to base 10. We need to convert that to binary. So therefore we start from the right hand side, 1, 2, 4, 8, 16, 32. That's as far as we need to go. So 32 actually we can cross off because that can't fit into 27. 16 can, so we put a 1 there. So we've got a remainder of 4, 11 left over. So we then see, does 8 go into 27? Yes, it does. That gives us a remainder of 3 left over. So 4 won't go into 3, and 2 will go into 3, leaving us 1 remainder, and 1 will go into 1, leaving us 0 remainder. So 16 plus 8 plus 2 plus 1, all added up together, equals our 27. So therefore our answer would be, and it says, doesn't ask for an 8-bit number, so we can just put it as a 4-bit number. So 1, 1, 0, 1, 1 to the base 2. That's that one. So question number 2 looked at or asked us, says using 4-bit 2's complement numbers, add 6 and 3 together and show all working. So we're going to use a 4-bit number. So 2, and basically, because it's 4 bits, 1, 2, 4, and 8. Now we must we must remember that this bit here in 2's complement is recorded as our sign bit. So there's actually only 3 bits that we've got to work with. So to represent 6 is that, and because it's positive, it's going to have the 0. So that is the equivalent of 6, and then 3 is the equivalent, once again, the sign bit is 0 because it's a positive number, no 4 and a 1 there, and we need to add those together. 1 plus 0 equals 1. 1 and 1 equals a 0, carry the 1. 1 and 1 equals a 0, carry the 1 again. 1 plus 0 equals 1. So that is our answer. That's all we had to do there to actually just to do that using 2's complement as our representing negative number system. That's all. So question 3, however, is what adds a bit of light to the problem. When a computer is used to perform the calculation in part 2, the results are not what is expected. Describe why this has occurred, including how this could be overcome. So the reason why it's not as is expected is because we know that 6 plus 3 equals 9, and obviously 8 plus 1 does equal 9. However, this is 4-bit 2's complement, so it's actually recording that as a negative number. So the sum of those numbers, instead of being positive 9 as the output, it's actually going to be minus 1. So that's why our result is not what is as expected. To describe why this has occurred is because we're only using 4 bits. The maximum that we can represent it into 4 bits is positive 7 all the way through to negative 7. Okay, so if we're to represent positive 9, we have to have an extra bit, so we would therefore need 5 bits, and we'd have to write that answer in the form of a description. So then we look at part B. So here we've got state of the truth table. For 2 marks, we need to name the device and its function. So we've got 2 inputs, A and B, which are then going to produce 2 outputs, X and Y. So from our knowledge of the content, to have the 2 outputs, our main type of circuit that this could be is either a half adder, a full adder, or a flip-flop, because we don't actually know what's going on here. It's definitely not a full adder, because a full adder normally has a third input. So it's either a half adder or a flip-flop. And in looking at what we've got here, so 0 plus 0 equals 0 and 0, 0 plus 1 equals a 1, 1 plus 0 equals a 1, and 1 and 1 equals 0 and a 1. So that looks like this is all the sums, and that's the carries. So name the devices described in the truth table above is a half adder. And don't forget the second barrel of the question, describe its function. So for B, we'd be looking at the device in the truth table is a half adder. Its function is to add two binary inputs together to produce a sum and a carry. Too easy for 2 marks. So now we're going to look at C. C is, and you can tell it's 5 marks, so it's a little bit more difficult. So it's talking about a security system has 3 sensors. So straight away, when we hear sensors, we should think inputs. Sensors are always inputs. Now, if a sensor detects a movement, it changes from being false to true. So it's going to activate itself, any one of those 3 sensors. So if one of those sensors is activated, then a light is going to turn to red. So the red light is our output. Now, so any sensor activates, then therefore our output is going to be the red light turning on. Now, this is where there's a bit of a curveball here. If no sensors are activated, then a green light is turned on by setting a true value to itself. So we've actually now got 2 outputs. So this is something a little bit different. Construct a truth table for the circuit that satisfies the above requirement. Draw the circuit for the security of the device. So the first thing I would do is to actually draw the circuit up, and would use Boolean algebra first to be able to construct that. Now, this is the important thing. So, and this is for C. Now, it's very, very important that we understand that we have, for the green light, sorry, the red light to be activated. So that will be turned on when A or B or C are active. Now, active means that they take their algebraic equivalent. So that's when red's going to be on. We also know that green will turn on when not A, not B, or not C occurs. So when the opposite of that occurs. So how do we then construct that into a truth table? Circuit. So we therefore know that we have 2 OR gates, and then we know that we can not the output of the original circuit up here to then therefore get the green output. So to start it off, we have our inputs, which are A and B. And I'm going to be doing this one here first. So here it is here. So A and B will be going into a OR gate. Too easy. Then the result of A and B will go into another OR gate with C. So I put C here, I flow it like this into another OR gate. And all of that should turn red on. Now if I grab the result of that, which is this green thing here that I'm looking at, and I flow that into a NOT gate, that should then get me green. So from my circuit then, I should be able to draw my data, my truth table, sorry. So with my truth table, I have A, B, and C as my columns. And I know that the sequence of numbers flows like this. 1, 1, 0, 1, 1, 1. And then I have my outputs. So I know I definitely want to find red and green, but I also want to find what is the output of A and B, which is this point right here. So A and B is equal to, going through an OR gate is equal to a 0, and basically what I'm looking at here is A and B. If they were going through an OR gate, what would be their output? So with an OR gate, whenever there is 1, the output will be 1. So all of those would be correct. It's only the first two of these, they're both zeros, that it therefore becomes a 0. Now, I should be able to find my red and my green for my truth table here. So, red is A and B with C through an OR gate. So it's always good practice to remember to put those two there. So 0 and 0 through an OR gate, rules are equals 0. 1 and 0 through an OR gate equals 1. 0 and 1 through an OR gate, 1. 1 and 1 through an OR gate equals 1. 1, 1, 1, and 1. Okay, for the green light, it will be whatever the opposite of red is. So it will be 1, 0, 0, 0, 0, 0, 0, 0. Come back to what we actually have to create first. So when it doesn't detect, if no sensors detect anything, then the green light will be active. If any of the sensors detect anything, then the red light will be active. So I come back to my truth table, and it basically shows here sensors are not active, so then therefore I have the green light on. When any one of these sensors is active, that will then show the red light which is on. That is 5 marks. Process pretty straightforward. Thank you.